Look around you for a second. Just take a look at, say, the casing of your laptop, or maybe the dashboard of your car.
Or even, just the perfectly smooth plastic of a regular ballpoint pen.
Right, exactly. Practically everything we use on a daily basis comes from a mold. And those molds, well, they're made out of hardened steel.
Which is, frankly, incredibly difficult to work with.
It really is. And here's the thing that absolutely blew my mind when we started prepping for this deep dive.
Yeah.
Like, how do you actually shape the hardened steel that makes those molds?
Yeah, you're taking one piece of metal and using it to violently carve out another piece of incredibly hard metal.
Right. And doing that without instantly destroying your tools or, ending up with just a warped, jagged mess. It requires a level of engineering that honestly borders on science fiction.
It really is the ultimate paradox of manufacturing. I mean, you need absolute microscopic precision, but you have to achieve it in an environment of extreme physical violence.
Extreme violence.
Yeah, you are dealing with tons of force, blistering heat, and relentless vibration.
And so that is our mission for today. We are unpacking the invisible physics of manufacturing. And this is all based on a really fascinating technical paper titled, "Why is the Fixed Beam GMC More Suitable for Machining Mold Steel?"
It's a great paper.
It is. We are going to explore how one specific marvel of engineering, the Fixed Beam Gantry Machining Center, or GMC, acts as the absolute foundation for creating the objects you and I use every single day.
So to kind of set the baseline here, the core problem is what happens when a cutting tool actually strikes hardened mold steel.
Right, because it doesn't just slice through like butter.
Not at all. The sheer resistance generates massive forces that literally want to push the tool away. If the machine holding that tool has an unstable structure, those forces translate directly into contour errors on the mold itself.
Which means ruined parts.
Exactly. You get ruined tools, and some factory worker ends up spending days doing this agonizing manual polishing just to fix the mistakes. Yeah, so the industry's answer to this is the fixed beam GMC. It's basically an architecture where the main overhead beam and its supporting columns are completely stationary.
Okay, so I want to start by looking at what it takes to simply survive the brute force of this process. Because before we can even talk about, microscopic precision, we have to look at the structural integrity required to just push metal through hardened steel without the machine itself bending.
Right, and that brings us to the concept of the rigidity chain from the text. It is a really fundamental principle in mechanical engineering.
The rigidity chain, okay.
Yeah, so when a spinning cutting tool hits a block of hardened steel, the steel pushes back with equal force. And that reactionary force, it doesn't just disappear.
Has to go somewhere.
Exactly. It travels up through the tool, into the spindle holding the tool, up into the ram, across the overhead beam, down through the vertical columns, into the machine table, through the metal clamps, and finally back into the workpiece itself.
So it forms like a complete physical loop.
A complete loop, yes.
So if there is a weak point, literally anywhere in that massive multi-ton metal loop, the whole structure is going to give way.
Precisely. Engineers call that elastic deformation.
Elastic deformation.
Right, which basically means the metal structure of the machine is physically flexing under the load of the cut.
Okay, to picture what elastic deformation actually looks like in practice, it's kind of like, imagine trying to carve a block of ice while standing on roller skates.
Yeah, that's a good way to put it.
Yeah, if your footing gives way, you lose your cutting force because the energy just pushes you backward instead of cutting the ice. Or another way to think of it is holding a heavy power drill at the end of a really long, flimsy fishing pole.
Yes, the fishing pole analogy is perfect because the machine's computer, the CNC, might command a cut depth of 2 millimeters. It tells the motors to drive the tool 2 millimeters into the steel.
But because the machine structure is acting like that flimsy fishing pole, it just flexes backward.
Right, under all that massive resistance. So instead of cutting 2 millimeters, maybe the tool only engages by, say, 1.5 millimeters. The tool is physically pushed away from the programmed path.
But the pole can't stay bent forever, right? If you are carving that wood and the drill suddenly hits a softer spot or the wood splinters, the resistance just drops.
And that is exactly the problem.
That bent fishing pole is going to instantly snap back to a straight position.
And that snapback is where the catastrophic damage happens. When the cutting load suddenly drops, all the tension that built up in the machine frame releases in a fraction of a second.
Oh, wow.
Yeah, the system springs back to its original position, which means the cutting tool violently dives deeper into the metal.
So it takes a huge gouge out of it.
Exactly. This repeated cycle of flexing away and springing back causes severe undercutting and overcutting. You end up with a mold that is physically just the wrong shape.
Which means the final plastic car dashboard or, the laptop casing you pour out of that mold is also going to be the wrong shape. So the goal is to make sure the machine frame never acts like a fishing pole in the first place.
Right. And this is why the fixed beam architecture is so vital. Older or, alternative designs often use a lifting beam
A
mechanism.
lifting beam.
Yeah, where the massive horizontal beam holding the tool can actually slide up and down on the vertical columns to get closer to the metal, which, it seems convenient for adjusting to different size blocks of steel.
Sure, it sounds flexible,
Ugh.
but sliding up and down requires moving parts,
Sure.
right? You need vertical positioning joints, sliding mechanisms, guideways, all that stuff.
And every single one of those moving joints is a break in the rigidity chain.
Ah, I see.
It is a potential weak point where elastic deformation can occur. The fixed beam GMC removes all of that. The horizontal beam is permanently cast or bolted directly to the vertical column.
No sliding joints at all.
None. It creates an immovable, highly stable bridge. And they combine this with a really thick, heavily reinforced ram and a very short spindle overhang.
So by eliminating the moving parts and keeping the tool close to the massive overhead beam, you drastically shorten the path that the force has to travel. You are basically replacing the flimsy fishing pole with a solid steel crowbar.
Exactly. That short force path allows the machine to handle heavy roughing operations.
Roughing is when you just hog out massive chunks of steel, right?
Right. Fist-size checks. And it does this without the machine flexing and without the delicate cutting, inserts chipping, or breaking.
Okay, I'm getting hung up on one thing here, though.
Yeah.
We just spent all this time establishing that this fixed beam machine is basically a fortress. It is bolted together, it has no moving joints in the frame, and it completely refuses to bend under pressure.
It is incredibly stiff, yes.
But if it is completely rigid, how is it possible that we still have to worry about vibration? Wouldn't a machine that stiff automatically just stop shaking?
It is incredibly counterintuitive, but rigidity and damping are actually two completely independent physical properties.
Really? Independent?
Yeah, rigidity is what limits how far a structure moves or bends when a force is applied. Damping, on the other hand, is the mechanism that removes the vibrational energy from the structure after that initial impact happens.
So you can have a machine that is as stiff as a board, but it still rings like a tuning fork when you hit it.
That is exactly the dynamic at play. A highly rigid machine with poor damping will refuse to bend, but it will endlessly transmit high-frequency vibrations throughout its entire frame.
Oh, wow.
And in machining, this high-frequency vibration is known as chatter.
Chatter, okay.
Right, because cutting hardened steel involves a spinning tool with multiple metal teeth repeatedly smashing into the steel thousands of times a minute, so you are constantly injecting this violent high-frequency energy into the machine's structure.
And if this goes wrong, it's not just a mathematical error on a computer screen somewhere. It means the physical mold ends up with tiny microscopic ripples and waves just carved into its surface.
Yes, visible ripples.
And when you inject plastic into that mold, your final product comes out looking like a wavy, textured mess instead of a perfectly smooth surface. And from what I understand, the only way to fix a rippled mold is to have a highly skilled worker spend days bent over a massive block of steel, just polishing it by hand.
It is brutal work.
Yeah.
But beyond the agonizing manual labor, chatter is just devastating to the tooling itself. Advanced cutting tools for hardened steel aren't just made of regular metal.
Right, they have to be harder than the steel they're cutting.
Exactly. They're made of specialized materials like solid carbide, ceramics, or PCBN, which stands for polycrystalline cubic boron nitride.
That sounds intense.
It is. These materials are unbelievably hard, so they can actually cut the steel, but that extreme hardness makes them highly brittle.
So they're structurally closer to glass than to standard steel then. Like, they can scratch almost anything, but if you drop them or hit them with a high-frequency vibration, they just shatter.
That is spot on. That constant ringing chatter causes microchipping along the microscopic cutting edge of the tool. And in severe cases, it causes a sudden, catastrophic fracture where the tool simply explodes mid-cut.
That's terrifying.
Yeah. So a fixed beam GMC has to address damping just as aggressively as it addresses rigidity.
How does it actually damp the chatter then? If bolting everything down tight doesn't stop the ringing, what does?
Well, part of it comes down to sheer mass and geometry. The fixed beam architecture utilizes these incredibly heavy cast iron beds and gantry frames designed with internal ribs and broad contact surfaces.
Just to soak it up.
Right, to spread the vibrational waves out and dissipate them. But the most advanced machines take it a step further by replacing standard cast iron with materials like mineral casting or polymer concrete in the base of the machine.
Wait, polymer concrete. So the foundation of this hyper-advanced $1 million steel cutting machine is essentially made of rocks and glue.
I know it sounds primitive, but it is a brilliant application of material science. These composite materials have fundamentally different molecular structures compared to, say, a uniform block of cast iron.
Okay.
So when the high-frequency vibration from the cutting chatter travels down through the machine and hits that polymer concrete, the complex granular molecular structure of the material literally absorbs the kinetic energy.
So instead of the vibration bouncing off the hard iron and echoing back up into the cutting tool, the polymer concrete just swallows it.
Exactly. It converts that kinetic vibrational energy into low-level thermal energy.
So it turns it into heat.
Yes,
Yeah.
it takes the physical shaking of the machine and turns it into a tiny, almost unnoticeable amount of heat. And by eating the vibration, the machine keeps the cutting tool perfectly stable. The physical path of that brittle cutting edge matches the digital path programmed into the CNC flawlessly, which leaves a mirror smooth finish on the steel.
That is unbelievable. So we've solved the problem of the machine bending, and we've absorbed the high-frequency vibration. We can cut a perfectly smooth, flat surface.
Yes.
But all of that assumes the cutting tool itself is short and stiff, right? What happens when the mold design forces you to use a tool that is, like, 10 inches long? Because if you think about the casing of a power drill or the interior door panel of a car, those aren't flat shapes.
Not at all.
They have massive, complex 3D topographies. They have deep structural ribs, narrow pockets, and really steep vertical walls.
And that is where it gets really tricky. Tool overhang is arguably the single greatest enemy of machining stability. When you transition from cutting the flat surface of a mold to reaching deep into a narrow cavity, the physics of the cutting process just change entirely.
Because the tool is so long.
Right. A long cutting tool behaves mechanically like a cantilever beam. And the mathematical reality of a cantilever beam is, frankly, staggering. The bending deflection of that tool rises rapidly with the cube of the overhang length.
Wait. With the cube. So if I have a tool sticking out of the spindle by, say, 2 inches, and I decide I need to reach deeper, so I swap it out for a tool that sticks out 4 inches, I've doubled the length of the tool. But the flexibility doesn't just double.
No, it scales cubically.
Oh, wow.
If you double the length, which is an increase by a factor of 2, the deflection goes up by 2 to the third power.
So 2 times 2 times 10.
Right. Your tool doesn't bend twice as much, it bends 8 times as much.
That is insane.
Yeah.
So a modest 2-inch increase in reach causes an exponential explosion in how much the tip of that tool is going to wave around when it actually hits the steel.
Exactly. That tiny bit of extra reach turns your precision cutting instrument into a wet noodle.
Okay, but I am seeing a logical gap here, though. If the tool itself is bending, because it's incredibly long and, it's physically impossible to change the laws of physics regarding cantilever beams, how does a massive stationary fixed beam way up at the top of the machine actually help?
It's a fair question.
Right. A rigid machine frame can't magically make a 10-inch steel rod stop acting like a 10-inch steel rod.
It can't. A fixed beam absolutely cannot make a long tool rigid. But what it does do is prevent unnecessary flexibility everywhere else in the mechanical system, which is what stops the errors from compounding.
Ah. So if the tool is already bending, the last thing you want is the machine holding the tool to start bending too.
Precisely. Imagine your tool is deflecting by 1/10 of a millimeter because it's long. That is already a significant error. But if your machine's beam is also twisting slightly under the load, and the ram holding the spindle is bending backward, all of those tiny independent movements just stack on top of each other.
That sounds like a disaster.
It is. Tool movement plus structural movement equals total chaos. The chatter goes through the roof, the cool shatters, and deep cavity finishing becomes entirely impossible. The fixed beam provides what engineers call a stable reaction structure.
So it provides an immovable anchor point so that the only variable you actually have to manage is the tool itself.
Right. And to
Right.
maintain that anchor point, they use massive square or box-shaped rams. That's the component that drops down from the overhead beam to hold the spindle.
Okay, why square?
Well, a square box shape provides incredibly balanced rigidity against both bending and twisting forces. Furthermore, because that ram is incredibly heavy, they use hydraulic or dual-cylinder balancing to physically support the sheer weight of it as it drops down into a deep cavity.
To keep it from just plummeting.
Exactly. This ensures gravity doesn't overload the mechanical feed drives, preventing any microscopic shuddering as the tool descends.
But even with all of that incredible engineering, I mean, a perfectly rigid fixed beam GMC can't just blindly plunge a 10-inch tool into hard steel, right? The mechanics of the machine have to be paired with human process strategy.
Absolutely. The machine is only as good as the instructions it receives. The human programmer has to be deeply strategic.
What kind of strategies?
Well, one of the primary techniques used is called trochoidal milling.
Trochoidal milling.
Right. Instead of driving the cutting tool in a straight line, just plowing directly into a corner where the tool would suddenly be surrounded by hard steel on multiple sides, the CNC is programmed to take these continuous, looping, circular paths.
Oh, so it takes smaller, rapid, spiraling bites out of the metal.
Yes, that's the
Nice.
cause.
That prevents the tool from suddenly biting off more steel than it can chew, avoiding those massive sudden load spikes that would cause a long tool to violently bend or just snap.
That's exactly the point. Another critical strategy is what they call rest machining. You don't try to carve the entire deep cavity with the long, delicate tool.
You probably break it instantly.
You would. So you use a larger, shorter, and much stiffer tool to rough out as much material as physically possible first. Then you only send in the long, skinny tool to clean up the exact spots, literally the rest of the material that the big tool couldn't reach.
Oh, I get it. The rest of it.
Right. The goal is to leave a perfectly uniform allowance of material on the walls of the cavity, so the delicate finishing tool never encounters a sudden, unexpected mountain of hard steel.
Which brings us to the final hurdle in this whole process. Because heavy roughing, delicate rest machining, and all these complex trochoidal looping paths, they take an enormous amount of time.
They really do.
Machining a large, complex mold can take 20, 30, even 40 hours of continuous nonstop operation. And where you have 40 hours of extreme friction, spinning metal, and massive electrical motors running at full load, you have one overwhelming byproduct, which is heat.
Heat is the invisible, creeping enemy of precision. And this introduces the concept of thermal drift.
Thermal drift.
So as the spindle spins at 20,000 revolutions per minute, and as the heavy metal axes are driven back and forth by the ball screws, and as thousands of hot metal chips fly off the workpiece, the ambient temperature of the machine's structure just gradually rises.
And it is a basic law of physics that when metal gets hot, it expands. It is kind of like a metal suspension bridge baking in the summer sun, right?
Great analogy, yeah.
If the bridge doesn't expand symmetrically, like if the sun hits one side and makes it hotter than the shaded side, the entire structure twists, buckles, and warps.
Exactly. And if a multi-ton machining center expands unevenly, the exact center point of your cutting tool slowly drifts away from where the CNC computer thinks it is.
Yikes.
Yeah, over a 40-hour machining cycle, the heat could cause your tool to physically drift by several hundredths of a millimeter. And in the world of precision mold making, that is a catastrophic failure.
So how does the fixed beam design defend against thermal drift? We already established it as a giant solid block of metal.
Well, it comes back to the architectural layout. A fixed beam provides massive thermal inertia. Because it is a large, stationary frame, engineers can design it with perfectly symmetrical cross-sections and balanced internal rib arrangements.
Okay, symmetrical is the key word there.
Right. When the temperature of the casting inevitably rises, both sides of the machine expand evenly in similar directions.
So instead of twisting and buckling like our sun-baked bridge, the entire machine just uniformly grows a microscopic amount in a predictable direction.
Exactly. It dramatically reduces the angular distortion between the cutting tool and the table holding the metal block. And this is another area where moving beam machines really struggle.
Oh, because of the joints.
Because machines with beams that slide up and down have heavy motors and friction-generating guideways built right into the moving beam itself. That introduces highly unpredictable heat sources directly above the cutting zone. The fixed beam architecture eliminates all those shifting heat sources.
But relying on the symmetrical shape of the metal frame is, well, It's passive. To survive a 40-hour marathon, these machines have to employ some incredibly aggressive, active countermeasures to physically fight the heat, right?
Oh, they do. High-performance GMCs are practically plumbed like living organisms.
Like a cardiovascular system.
Very much so. They don't just use fans. They circulate chilled oil or water continuously around the spindle casing, around the electrical motors, through the bearing housings, and incredibly, they even pump refrigerant directly through the hollow centers of the ball screws that drive the heavy axes.
Wait, they are literally pumping chilled fluid through the moving skeleton of the machine
Yes,
just to extract the heat before it can soak into the cast iron frame.
that's the goal. They also isolate the external heat sources. So the hydraulic pumping stations, the electrical cabinets, the fluid chillers themselves, they are physically unbolted and moved away from the main machine frame.
Just keeping them at a distance.
Right. This ensures their radiant heat doesn't warm up the surrounding air and alter the casting's temperature.
And the environment around the machine is just as critical from what I read. Precision mold shops operate like laboratories. They keep their ambient workshop temperature locked at a constant 20 degrees Celsius year-round.
They have to.
But the most mind-bending countermeasure to me is how the CNC computer handles the heat it can't extract. The machine uses a digital thermal model.
Yes, this is where mechanical engineering meets advanced software. The machine has highly sensitive temperature sensors plastered all over its physical frame. These sensors continuously monitor the thermal gradient of the casting.
Okay.
The CNC computer takes that temperature data and calculates in real time exactly how much the cast iron is expanding or distorting on a microscopic level.
And once it knows that the metal frame is grown by, say, 0.02 of a millimeter, the software seamlessly alters the coordinate toolpath mid-cut. So it physically shifts the motors by 0.02 of a millimeter in the opposite direction to perfectly cancel out the thermal drift.
It is a breathtaking synthesis of hardware and software. They go to such extreme lengths for stability that they even age the massive resin sand castings before assembling the machine.
Age them. Like wine.
Kind of, yeah. They will leave the raw cast iron frame sitting outside in the elements for months, or bake them in massive industrial ovens just to relieve the internal residual stresses in the metal. They ensure the iron has completely settled into its final shape before they even begin machining the mounting surfaces.
Wow. We have covered some serious ground today. Making the things you and I use every day requires machining hardened steel, and that process is an uncompromising, brutal battle against the laws of physics.
It really is.
We learned that the fixed-beam gantry machining center wins this battle on 4 distinct fronts. It uses massive, immovable structural rigidity to fight the brute force of the cut and prevent elastic deformation. It uses advanced polymer concrete materials to absorb high-frequency chatter.
Right.
It utilizes a rock-solid, balanced box ram architecture to provide an anchor for long, delicate tools reaching into deep cavities. And finally, it relies on symmetrical thermal inertia and active liquid cooling to survive a 40-hour marathon without warping.
It truly is the unseen, highly engineered foundation of the entire manufacturing world.
So the next time you pick up a perfectly smooth plastic device, or you run your hand along the precise, sweeping contours of your car door, you aren't just feeling a piece of mass-produced plastic or sheet metal. You are feeling the direct result of a massive, perfectly tuned, thermally stabilized, fixed-beam machine that fought its way through solid steel for 40 hours just to make that precise shape possible.
And if we look toward the future, this raises an incredibly fascinating question to mull over. We established that while these fixed-beam machines are incredibly advanced, we still rely heavily on human process strategy.
Right, the trochoidal looping and the rest machining.
Exactly, the programmer picking the right path or perfectly managing the stock. But as CNC systems get exponentially smarter with real-time digital thermal modeling, and as they get faster at analyzing high-frequency vibration and altering the toolpath to compensate for it instantly, will we eventually reach a point where the machine perfectly adapts to any flawed human strategy in real time?
Oh, that's an interesting thought.
Or will the new alloys and aerospace materials we invent simply become so impossibly hard that this entire battle of physics just starts all over again at an even higher, more violent level?
That is a brilliant thought to leave off on. Are we eventually going to engineer our way out of the problem, or are we just going to keep fighting on harder and harder battlefields? A huge thank you for joining us today and letting us unpack this incredible hidden world of manufacturing. Keep questioning, keep learning, and we will catch you on the next deep dive.